This is about memory management in the JVM. And I hope it's interesting. I just gave it yesterday in the Netherlands at JSpring. And it's all about memory management in the JVM. That means garbage collection, but I hope in a way that everybody understands it. Is someone here a professional in garbage collection stuff? Okay, great. My name is Gerrit Grunwald. I'm working for Azul. We do JVMs and all things Java. And to directly start, because we just have 50 minutes, memory management in the JVM. It is automatic, right? So why care? Who's here in the audience really setting explicitly a garbage collector in production? One. And the rest is just trusting that everything's fine, right? Which is good. It's a sign that it works, right? So that people did the right job when they created the garbage collectors and the default garbage collectors. So nevertheless, garbage collection has an impact on application performance, on responsiveness, and also on system requirements in your application stuff when you run it. And to give you a very quick, simple overview how it works is, this is how it's structured in the JVM. So for each thread, we have a so-called stack frame, which you see on the left side. And this one contains primitives and references to objects, right? And it grows and shrinks automatically. So there's no garbage collection needed there. And it's also thread safe because it's local access only. And if you get a stack overflow, that means this stack frame runs out of memory, right? And then we have the heap. The heap is has shared access, so it's not thread safe, and it needs garbage collection, and this contains the actual objects, right? So then we have the meter space, and the meter space is, to make it short, it's really just for the JVM. It contains all the information about classes, right? So this is all handled in the meter space, and we don't want to focus on that one. We focus on the center, right? To give you an idea how it works, this is some little piece of code as a record, and then I have some instances of this person, and then I put the references into a list, and when I print out P1, then it prints out Gerrit. Perfect. This is the stack frame for that. It contains the references for all these objects that are created, right? And these references point into the heap. And in the heap, we have the actual objects, right? And each reference points to these objects, okay? This is how it works with the stack and the heap. And now all of these objects are reachable. All the red ones can be reached from the stack frame, right? So they are live because I can reach them. So if I now set the P1 to null, then you would expect when I print out P1, it's null, okay. But it's still reachable. It's still live because there is a reference in the list, right? So if I print out, if you see on the left side, persons get 0, it will print Gerrit because it's still in a live object in the heap, even if the object itself is null, okay? Good. If I now set the persons to null, then only these 3 objects are reachable from the stack frame, and the rest is garbage. This stuff is lying around in the heap, still taking some memory, but it's not used anymore because you can't reach it from anywhere, right? Okay, that's how it works in principle. And that leads me to garbage collection in general, which is a form of automatic memory management. We all know that. It identifies and reclaims no longer used memory, ensures efficient memory utilization, and this is the most important part. It frees the user from managing memory manually. So who has a C++ or C background here? Then you all love the malloc and free stuff, right? It's awesome. So this should take the pain away from you, but still it doesn't come without problems. And to get a better understanding how it works, if we talk about precise garbage collectors, then we can split the process of garbage collection in 3 phases. And we start with identifying live objects. First, we have to figure out what is live. What can I reach from the stack, right? This is so-called tracing. And the next step is reclaiming these resources. So that means stuff that is lying around, but I can't reach it anymore. So the dead objects, I have to free the space, right? Because otherwise I will run out of the heap space, which is the out of memory exception. So this is freeing. And then from time to time, I have to do some kind of compaction, because what will happen, so who knows or who remembers Windows 3.11, right? There was this disk fragmentation. You probably all know that. The same stuff happens on the heap. So we have to defragment the heap. That means compaction. But I have some demos to show you how it works. And we need to have a very brief look at the basic principles of collectors. I don't mean the garbage collectors in the JVM. I mean the basic principles. The first thing is there is a so-called non-moving collector, right? It's also called mark and sweep. Who heard about mark and sweep? Probably most of you heard of it, right? So it's pretty simple. I give you an idea. You see, this is my heap. The gray areas are free cells. If they are blue, they are live. So there is a reference to them. If they are purple, they are dead. So the reference is gone and they are just lying around. It's garbage. If they have this little red square on the upper left corner, that means they are marked as live objects. And if they have a number inside, that means they survived the garbage collection cycle. So that means I have an object and it's still reachable. I do a garbage collection and the object afterwards is still reachable. That survived a garbage collection cycle, and this is the number. So what you will see on the left side, you see already the procedure. So we will see allocating memory. When the heap runs out of memory, we stop the world. We mark all the live objects. We free the dead ones. And then we continue. We unmark and we continue. That's the idea. Let's have a look. If it starts working. Oh, it does already. OK. So you see it starts allocating, and objects die after some time. It's the purple areas. And now we run out of heap. So we have to stop the world. And this happens now. We mark it, unmark, and then continue. And you see what happens here. This is the Windows 3.11 effect, right? It's fragmentation. So this is the very simple example where every object is just one cell. But in reality, it's not the case. That means if we would have a big object that needs 4 cells, then it gets harder and harder to find these 4 cells, right? Because we fragment the heap by all this deleting dead object stuff. Okay, so you see, it's already now, it's hard to find these spaces. There are some, but if you fill them up, this is the hard part. So mark and sweep has this fragmentation problem. It's fast because we don't have to move stuff. We just mark them, and everything that's dead will be removed. But it comes with the problem of fragmentation. So that leads me to the next one, which is a moving collector. Moving collectors we have 2 different kinds of. So the first one is the so-called mark and compact. It's a compacting collector. It's very much the same that we saw before, right? It's the same thing, but instead of just removing the dead objects, now we remove the dead objects and then we compact all the live objects to the left side. That means we copy all the objects to a new position. And then remember what I told you. There's this reference from the stack pointing into the heap, right? If we move the object, we also have to update the reference, because otherwise it will point to some area, okay? So that means it's an additional effort we have to do. We have to copy stuff and update the references, okay? But you will see it's the same procedure, just with one additional step. We allocate memory. Stuff dies after some time because it's not used anymore. And now what will happen is we will see stop the world, mark, free, unmark, compact. Mark, free, unmark, compact. Continue. You can already see it's way easier now to allocate memory. Even if we need large spaces, it's always available because we have this compaction stuff, right? So we get rid of the fragmentation here. That's the advantage of using a compacting collector. But it comes with the additional step of copy stuff and updating references, which is the drawback, okay? So, means we have a problem here, which is, first of all, we need more headroom. Headroom means we can't just fill it up completely. We need some space to copy stuff around, right? To make sure that we can everything, compact everything to the left side, we maybe first have to make some space on the left side. So we need some space to copy it first, move stuff over, back and forth. So that means we need a little bit more space for mark and compact. That's the headroom. Okay. Next one. And this is nearly the last one. And then you're done with these different principles. But believe me, it will be more complex afterwards. Mark and copy. So we saw mark and sweep, mark and compact. Now we do mark and copy. Mark and copy looks different. Looks like this. So instead of having one heap space, suddenly we have two. And it's the so-called from space and to space, because we start allocating on the left side here, right? When we fill up the left side and it's full, we find the live objects, and then we copy all the live objects to the other side, right? And then we can just completely free the left side, because everything that's in there is then garbage, right? And then when we also toggle the space, so the to and from space, you will see they will toggle colors every time we do that. So just let's have a look. So we allocate, and when we run out of memory in the to space, you will see the spaces will toggle. We mark the live objects, we copy them over, and then we just clear the complete former to space. So now it's toggle, mark, copy, clear the left space, continue on this side. This means this is automatically compacting every time we copy stuff. That's an advantage here, right? Because we don't have to explicitly do the compacting, because this is automatically compacting when we copy stuff between the to and from space. You might have heard survivor spaces somewhere. We will come to that. This is exactly the collector that is used there. Okay, you also directly see the drawback. First of all, we need twice as much memory, because if one of the sides has to be it's a heap, right? To be able to copy it, we need the same amount again. So that means we need twice the amount of memory for the same heap thing that we would like to address. But the other problem is, if we have objects that live for a long time, we have to copy them every time. Because they live forever, then you have to copy them with every garbage collection cycle. Copy objects, remember, it's also updating references all the time. So this is the drawback. That means long-living objects and twice as much memory. That's the drawback of this collector. And that leads me to a more practical approach, which is the generational collector. Did someone ever heard about generational garbage collection? Yes, this is how it works. This one is generational mark and compact, because it was used in the JVM for some time, and it's based on the so-called weak generational hypothesis. That means objects die young. This is not something that some scientists came up with, but they found that out, and this is not only for Java, this is for all the languages. In principle, this is the chart. If you allocate objects or memory, most of them will die shortly after. And then we have some objects that live for a little bit longer. That's the medium living objects. And then we have very few that lives for a long time. Right? And if we know that, then we can shape the heap according to this behavior. And this is done by creating, for example, an Eden space where we create objects. It can be small, because objects die young. It's not a lot of objects will survive in that space. And then we have the so-called survivor spaces. You see already that's a copy collector. And then we have a huge area, which is the to-nerd space. And this is usually also known as the young generation, is the Eden and the survivor spaces on the left side. And on the right side, you see the old generation. Old generation means objects that survived a couple of cycles of garbage collection. And if we talk about garbage collection, you stumble often upon these words like, oh, we do a minor collection. What does it mean? A minor collection means it's only the young generation, Eden and survivor spaces. If we talk about a major collection, it's only the old generation. And if we talk about a full collection, then it means both of them. Right? So that's the difference, because sometimes major collection and full collection will be messed up. Full collection is everything, young and old. Minor is only young, a major is only old, okay? And then, again, a little demo, a little bit smaller here. So you will see the same behavior that we saw before. I will allocate in Eden. When Eden is full, I will mark stuff, copy it to the survivor space, to the 2 space, and this will continue until the 2 space is full. Then we do this copy thing that we do when we use the copy collector. And if an object survives more than 3 cycles in this example, it will be promoted, that's the word, promoted to the old generation. And with this functionality, we avoid that we have to copy long-living objects all the time, because once they are old, we just move them to the old generation and keep them there. And the old generation is huge. That means we only have to do a garbage collection in the old generation when it runs out of memory, and that can take some time. Okay, let's have a look. Does it start? Yeah. So first it's slow, and then I will do a fast forward, so then you can see on the old generation, it's like a wave front moving through the old generation. You see we fill up the 2 space, and then do the copy, and so on. And now, in a few seconds, you will see we do the fast forward, that you see how it works. If objects getting older than 3 garbage collection cycles, they will be promoted into the old generation. And now we do fast forward. Now you can see how it works. And you see, even in the old generation, objects die after some time. So we have this wavefront moving. And if this is full, we have to do is stop the world, mark in the old generation, clean, compact, and then we copy everything from the young generation over. Now, full, we mark, clean, unmark, compact, and then we copy everything from the young generation into the old generation, and then we start from scratch. This is how a generational collector works in principle. This is very basic, simplest approach, but I think you get an idea how it works, right? And this is all, and you see, this is always stop the world. When I say stop the world, means you have an allocator that is maybe your application thread, and it needs memory, so it's allocating stuff. When we run out of memory, we have to stop the world. That means no thread can access the memory anymore except the garbage collector. And then the garbage collector does its work, and then we say, okay, now you can continue, right? This is stop the world. Okay, I told you we do a minor collection only in the young generation, okay? There's one problem here. If we do that, and now we have a reference from the old generation that points into the young one, well, hard to imagine. Let me give you an overview. So we have the stack frame, the roots, we have the young generation and the old generation. We do a minor GC on the young generation. This is all the references that we know, right? That's all good. But now there is this one. Because we only do the garbage collection in the young generation, how do we know that the one with the question mark, how do we know that this one is live? Because in the young generation, we don't see that there's anything pointing to it, because this is coming from the old generation. So that means we need some kind of a process to make sure that we find these references. And this is called a so-called mark table, or also the remembered set. This is, like I said, this is a very simple approach, but this is used everywhere. So if you stumble upon remembered set or card table, this is what it means. It's the functionality to keep track of references that are intergenerational, right? Because we do garbage collections in the generations differently. Could be even a different collector, and it is. In the young generation, we saw we use a copy collector, and in the old generation, we used mark and compact, right? So this is the principles that we saw. Okay, so the GC looks up the card table, and then it finds the reference, and then it can mark the one as live. So this is how it works. It's just to remember. It will be more complex, believe me. That's just the easy part, because now, what about concurrent collection? So this was all stop the world. It's easy, because we can just hold everything, clean it up, and then continue. But if we have to do that at the same time where the allocator is allocating memory, and at the same time we clean it up, you can imagine that leads to some kind of problems, because concurrency is hard. And if we take a look at concurrent marking, marking is the process where we follow the references from the stack frame, and then we mark all the objects that we can find as live, right? That's the idea. Then let's take a look at this one. We start with the stack frame, that is the root, the square, and we have a reference that points into the heap. So that means, okay, we just follow the reference, and then we say this object I can reach That's good. Next step is I mark it as live. That's the white circle. And then we go to the next one. Gray means I reach it, and then the white one means I mark it as live. You see there is a reference from the gray one going down. If it's now concurrent, that means at the same time where we do this process, the allocator can decide, you know what, I just remove the reference and I create a new one, like this. The collector is already, he passed the first circle, so he doesn't know that there is a new reference. And he continues. So, okay, I just go ahead, mark all the stuff that I can see, and because the red one was removed, he can't see it anymore. So he marks everything, and then this would be removed by the garbage collector because it doesn't know. So we have to find a way to make sure that the garbage collector can find these references when we do concurrent marking. So how can we do that? Well, there's a principle called barriers. Did someone ever heard about barriers? Yeah, there are write barriers and read barriers. And to make it as simple as possible, it's not really that hard. In principle, it's a piece of code that will be executed every time you access a memory cell, either for reading or for writing. Right? That's the main idea. What you do in this code, up to you, right? Or the garbage collection developer. And you can use that to keep track of intergenerational stuff, right? The things that we saw with the card table, you can also use barriers to do that. You can also use it to synchronize the action between the allocator and the collector. That's the idea behind it. And one thing you have to keep in mind, if you use read barriers, you have to be careful, because if you have the ratio between reading memory and writing to memory, it's around 80% to 20%. So that means 80% is reading, 20% is writing. It means if you have a read barrier, that means on every read, you have to execute the code. So the code has to be very efficient, otherwise it will drag down the performance, right? If we go back to the example, then we do the same stuff as before. Reachable, yep, marked it as live, reachable. On each cell is now a write barrier. I just put it here in one because otherwise the diagram would be too much filled up. And now the allocator steps in and removes the reference. But to do that, it has to execute the code in the write barrier. And in this example, the code says, if you remove a reference, then mark the former live object as reachable. This is what it does now. It marks this one, yeah, you can reach it, right? And then what happens is the collector continues collecting all his live nodes, and once it's done, there is a second phase. It's a remarking phase, right? So then the collector, once it's done with his marking phase, it goes again through all the stuff that was marked in this time in between by the write barriers. And then it finds this one, can mark it as live, and we are good to go. So this is one example for a write barrier, right? There are way more complex ones, but this is one way how you can use it, how you can overcome the problems when you do concurrent garbage collection. This is only marking, right? So it's also called snapshot at the beginning. Sometimes you see this expression. Concurrent copying, that's even harder. Remember, we have, for example, the copy collector. So we copy stuff every time we do a garbage collection. We change the position in memory. We have to update all the references that point to this new position. So if this is our object, and we have the references pointing to the header here, and we do stop the world copying, then we stop the world, easy peasy, copy the object to the new position, no problem. We install a forwarding pointer in the header, and then we update all the references to the new location, and once we are done, we can remove the old one and say, okay, continue. Let's stop the world, easy, okay? If we do that concurrently, it's a little bit more complex, because then what happens is, same thing. We have the object, we copy, but now we didn't stop the world. That means both objects are suddenly reachable in memory. If we now start updating references here, right, then it means, oh, this is reachable there, and the other one is reachable there, and if threads start to write stuff into the objects, one will write here, and the other one will write there, right? because you don't know which is the real one, which is the live one. This happens all concurrently at the same time. So we need a process to make sure that we can only copy to the new one until all the references are updated, right? One way to do that is the so-called Brooks pointer, right? So this is, oh, it's not here? There it is. So instead, before we do the copy stuff, we install a forwarding pointer in the original object, and the pointer points to the object itself. That sounds, in the first step, sounds a little bit silly. Why would you do that? Right? Because it doesn't really help. It helps us exactly now. Because now, when we copy the object, and we didn't update any references yet, then everything's fine still. And what we now do is, we just, oh, why isn't it? This forwarding pointer, then we just pointed to the new header. And for this moment where we do this, we stop the world. But this is so shortly that we can ignore it. That's the reason why I don't really show it here. And then we can update all the references, because then what happens is, if an object accesses this one by the new reference, no problem. If another thread goes to the old one, it will be forwarded automatically to the new one, right? So this is how you do concurrent copying if you use a Brooks pointer. And then once all the references are updated, and this is something that you have to keep in mind, first you have to update all the references. The reason for that is that the information is in the old object, in the header, the forwarding pointer. And only if all references are updated, then we can remove it. Removing means also freeing physical memory below that, because we talk about virtual memory here, right? This is all memory mapped. It's not really that we address physical memory cells here. We address virtual memory that is mapped to physical memory. But to be able to free physical memory, we first have to remove every reference in the old object. That's important. And then we can remove the old one. And then everything's pointing to the new one. Believe me, it gets more complex. But so if you're still awake, it's great. Now we come to the collectors in the JVM, because we have different ones here. We start with this one. It's the serial collector. It's one of the default collectors that we have. We have only 2 default collectors at the moment. This is one, and the other one is G1. So because my original slide deck was 270 slides, and that doesn't really fit into a session, I had to compress it a little bit. So this is the reason why I have this more overview style slides here. So the serial collector is one of the oldest one, and doesn't mean it's a bad collector. And how it works is, you can think about, you have, for example, 10 threads, and these 10 threads work on your application, right? So you fill up your heap, you need a garbage collection, you stop the world, and then you have one thread, and this is doing the garbage collection, and when it's done, we just continue with the 10 threads for the application. This is the serial collector, okay? And this one will be chosen automatically if you do not define explicitly a garbage collector. The JVM will make its own decision, right? And this is based on the heap size and on the hardware that you use. So for example, if you run on one CPU only, you will get the serial collector, right? Or if you have less than 1.8 gigabytes, you also get the serial collector. Usually this is no problem, but if you run, for example, a microservice and in a Docker container, in a container, and you would like to have it on a very small node, and you choose, this service is not really important, I just need one CPU and I just need 1 gigabyte of RAM, it's fine. You will get this collector. You can choose a different one, but believe me, this is the best for this use case. It's just that you are aware, if you not define a garbage collector, this one will be chosen by the JVM automatically if you have very small nodes in your cluster, for example. And as I said, it doesn't mean it's a bad collector. Okay, that leads me to the next one, which is the parallel collector. And the name already says it. And if I told you the serial collector does, for example, 10 threads, stop the world, one thread does the garbage collection, and then we continue with 10 threads, the parallel one does more or less the same, but it does stop the world with your 10 threads, and it takes the 10 threads for the garbage collection, and then it continues. That means, and this is also the reason why this collector is called the throughput collector. The throughput is the ratio between time you spend in garbage collection to time you spend in application. The more time you spend in the garbage collection, the lower is the throughput. And because if you use all the available threads for garbage collection can be quite fast, and you spend not a lot of time there. So this is the reason why this is the so-called throughput collector, and it's a really good collector. If you have multi-core systems with small heap, it's not too bad. And if peak performance is needed without pause time requirements, because the problem still, we have stopped the world, right? We can't really say when it will stop, and it can stop, and it will stop maybe for a little bit longer, depends on how large the heap is. This is the problem with this kind of collectors. If you have a large heap, let's say you have 128 gigabytes, it takes some time until it fills up, right? But once it's filled up, you have to do a garbage collection on 128 gigabyte, and that takes some time, right? So that's the problem with the large heaps and these older collectors. It's good for batch processing, scientific computing, or data analysis, and this is the switch, how you can switch it on. And you see the CPU overhead is quite low with this collector, which is a good thing. And it was the default collector from JDK 5 to JDK 7. So when you didn't choose anything, that was the one. By the way, someone's using still 6 or 7 here? Nobody? 1? Okay. And then there is another one, which is called CMS, and this is already deprecated. Concurrent mark and sweep. And this is exactly the generational collector that I showed you. This is how it works, but this works also concurrently. It can do concurrent marking. But the setup, so the design of the collector was very much the same that I showed you. Okay, so it's deprecated. Yeah, that means it was removed, or it was deprecated in JDK 9, it was removed in JDK 14. So if you are on 17 or above, you can't even select it anymore. It's not in the JDK anymore. Reason for that is there have been some problems. It was not really reliable in all situations. So it doesn't mean it's a bad collector, but you see already CPU overhead increases a little bit because it has also concurrent parts in there. You see it's partially concurrent. It's generational, like all the collectors in the OpenJDK except one are generational. And yeah, it's good if your response times is more important than throughput, and the pause time must keep shorter than 1 second, and this was a good collector, right? So for web application, medium-sized enterprise stuff. And as I already mentioned, it was deprecated in JDK 9 and removed with JDK 14, so it's not part of the JDK anymore. And there is a successor for that, which is called G1, right? Garbage first. This is a very specific collector because it's different from all the other ones. We saw how the heap was structured with the Eden, survivor spaces, and the to-nerd space. That leads to problems if you have larger heaps. Because if the to-nerd space gets really big, let's say we talk about 512 gigabytes, something like that, garbage collection takes forever. Right? It can really be in multiple seconds. And you don't want to stop your application for seconds, your web shop on Black Friday. Just, oh, sorry, we do a garbage collection for the next 20 seconds, sorry. The new approach is it's a so-called region-based collector. Instead of having fixed size regions, we have all these tiny regions, and they are related to the heap that you give it with minus XMS and XMX, for example. If you say your heap is smaller than 4 gigabyte, then one of the regions is 1 megabyte. If it's larger than 64, then 32 megabytes, each of these regions is 32 megabytes. And then what happens is if we start collecting or allocating, we just take a region and fill it up slowly, right? In the same way we saw before, right? We allocate in that region, objects will die. If it's full, we just take a next one, and so on. Because there's a specific ratio between young and old generation. In this case, it's between 5 and 60%. You can define it. So we take regions as long as we are allowed to, and at some point, the JVM says, okay, now you have enough Eden space allocated, so now we have to do a collection. It finds the regions that have the most garbage. That's the reason for garbage first, right? It's G1. That means the less amount of live objects in these regions, and these regions will be collected, garbage collected. That means that it takes the live objects out of here right? Copy it into a survivor space. We don't have this to and from space here, we just have a survivor space. That means in this space are all objects that survived the garbage collection cycle, right? And then we continue. It looks, at some point it looks like this, and then if, for example, the survivor space is full, then it will become a tenerd space. We copy all the stuff or promote it in the tenerd space. And then we remove the survivor space. So that leads to the fact that at some point the heap looks like this. So it's completely split it up. It has a really big advantage because we never have to look for free areas because we always have enough free areas of a specific size, right? And if you have really huge objects, so-called humongous objects, right? If they are larger than half the region size, they get their own region. They will directly be promoted to the old generation, so to avoid copying around big objects, right? So it will directly be an old generation object. Okay, that was the first collector in the JVM that came with this region-based approach, and all the others that came afterwards have the same. So this is the new thing of the new way of doing things. And yeah, it's more or less the same that CMS. So its response time is more important than throughput, and the pause times have to be kept below 1 second. Then this is the collector to go. This is the default garbage collector at the moment. So if you don't specify garbage collector, you use this one. And it looks like most of you do that, and you are happy. So that means it's not really a bad collector. Okay? You see already CPU overhead, it's a little bit higher now, because also G1 does partially concurrent marking. Right, so, all right, as I said, default collector from JDK 9 onwards. Who knows that one? Epsilon. Oh, 2 people. Epsilon is a very interesting collector because it's the no collector collector. This is no garbage collector at all, which sounds now a little bit stupid, right? So why do I need a garbage collector that doesn't do garbage collection? The reason is, let's say you would like to measure your application performance, really the performance of your code. If you do that normally and you use G1 or whatever garbage collector, then you always measure the garbage collector with it because garbage collection will take place, also when you monitor your application. If you're interested in the performance of the code only, you use, for example, Epsilon, because then there is no garbage collection. It's pure code running. The problem is, if you run out of heap, out of memory exception, because there's no garbage collection. So that means if you use this one to measure your stuff, make sure that you really know how much memory you need. Otherwise, you will always run in out of memory exceptions. It can be frustrating. And if you are really good and you have very small microservices and you know exactly how much memory they need, you can even use it in production, because then you run your code without doing garbage collection at all. There are some companies that do that, but you really need to know exactly how your code is behaving. Otherwise, you run out of memory in production, which is not a good idea. Okay, this is only available in OpenJDK. The other collectors are, I wouldn't say they are also available in OpenJ9, but they have very similar collectors. But this one is nothing similar to this one is available in OpenJ9. So this is only in OpenJDK. Okay, next one. Shenandoah. This is a collector which is relatively new, and it was developed by Red Hat. Roman Kenke did that, and he's now at Amazon. That might be the reason why this is the only collector which is not generational. He started with it, and there was a proposal, and it never made it into OpenJDK, probably because he moved to Amazon and didn't work on the Red Hat stuff anymore. That's my idea behind it. This is a fully concurrent collector, which uses a new principle, like a read barrier everywhere. And they also use Brooks pointers. And it's made for response times that should be, so have a higher priority, means very short breaks. I think they guarantee below 10 milliseconds for the garbage collection pauses. And it's made for very large heaps, so you can address really huge heaps, right? Okay, so it's for highly concurrent application, large-scale systems, and latency-sensitive applications. You see the CPU overhead is already bigger now, right? This is one thing you have to keep in mind. As soon as we talk about concurrent garbage collection, means you have 10 threads, right? They work on your application. And now you have, let's say, serial garbage collector. Then we stop the world, we do the garbage collection, then again we have the 10 threads. If we use a concurrent garbage collector, we have 10 threads. They work on the application and on the garbage collection at the same time. So that means the performance is always lower because the impact on the CPU is higher if you use concurrent garbage collection. You have to keep that in mind because, for example, Netflix, recently they changed everything to ZGC. I will come to ZGC in a second. And they saw a drop in performance of 3%. That sounds not like a lot, but if you're as big as Netflix, then 3% of the whole stuff, you have to spend more money to keep up with the performance. And that could be quite an amount of money, so you have to keep that in mind. So concurrent garbage collection always comes with a drop in performance a little bit. All right. This is not available in Oracle JDK. So is someone using Oracle JDK here? I mean the Oracle subscription, not the Oracle Open JDK, because you can't use it. And the reason is probably because it was invented by Red Hat and not by Oracle, and they don't like it. So yeah, we have a little bit reduced throughput due to concurrent GC, and it makes use of the new barrier concept, which is the loaded value barrier. Leads me to this one, ZGC, which is the newest one in OpenJDK. Again, very similar to the idea of G1. So we have regions, we have young generation, old generation. If a young generation ages, aging means surviving garbage collection cycles, it will get promoted to the old generation. So that means it will become an old generation region. We don't have survivor spaces in ZGC. And also, these are not separate spaces. This is one space. It looks like this, something like that. So this collector is, again, different. This is fully concurrent. You see it has a higher overhead for CPU. This guarantees response times below 3 milliseconds, as far as I know. And it's made for very large heaps, so we talk about terabytes. Now you might think, okay, terabyte heap, never heard of it. So one of our customers is using a 21 terabyte heap. When I heard that the first time, I had to ask again, so do you mean gigabyte or terabyte? No, it's terabyte. It's 21 terabyte, and we do 0 downtime garbage collection cycles on 21 terabyte there. So this is possible, right? And this is with these collectors. I don't go into detail. So this will probably become the default collector in the future at some point. At the moment, the default in JDK 22 is the non-generational version. If you would like to have the generational, you have to switch it on with this Z generational flag. With JDK 23, this will be, the default will be the generational one. So the non-generational version is already deprecated, so it will go away, right? And that leads me to the last one, which is C4. And this is something that we invented at Azul already 12 years ago. This is the so-called concurrent continuous compacting collector. That's for C4, 4 times C. It's only available in our own JVM. The reason why I mention it is ZGC is more or less a copy of this collector. It's really one-to-one the same thing. So it's the same algorithm and the same idea behind it. Just the generational ZGC is a little bit different than ours. But the principles are the same, and that's the reason why I can explain both with the same slides. So yeah, if you are on Linux, it makes a lot of sense also for ZGC using transparent huge pages, which is the memory page size in Linux. That helps the collector because this is bound to the memory page. And if we take a look at the marking phase here, then it's a little bit different. This also is true for ZGC. You see the orange threads. This is GC threads, garbage collection threads, that are working concurrently to the application. They find the live objects, right, marking them in the heap, and you see always this LVB, which is the loaded value barrier. In ZGC, it's called colored pointers, but it's exactly the same. Technically, no difference. And then what happens is it marks all these objects live, and suddenly the application thread steps in and says, oh, you know what, I will allocate this memory cell. And now we have the loaded value barrier, so that it's a read barrier, and the read barrier will be triggered as soon as the application thread allocates it. And then we do something called test and jump. I told you if you do read barriers, you have to be very fast. And we can do that in one CPU cycle. And the test and jump means we check if it's a reference, and if it's a reference, we jump to the position. If it's reachable, it's fine. If not, then we just make it reachable. And then we mark it. And the difference now is, with these collectors, the application thread also marks objects as live. It's not only the collector. That means we don't have to do remarking phase, right? So it marks the object, and then it tells the GC, you know what, here's another object, you can just use it. It's live. I allocated it. So the allocator and the collector working hand in hand. That's the difference in ZGC and in C4. And if we take, so there's no need to do the remark again. So we save this remarking step, which makes it faster. And to give you the totally complex overload now, it's if we do remapping with quick release using a loaded value barrier in the lower part, then what we do is, instead of moving, let me see, we copy the object. Instead of moving the forwarding pointer to the old object, as we saw before with the Brooks pointer, we just move it outside of the heap completely. We put it in an off-heap area, and then we can update, this updating the references will be done by the loaded value barrier. Every time something tries to reach this header, the old one, it will automatically use the forwarding information from the off-heap page and point to the new one. And even if the application thread is now trying to access the old one, it does the test and jump. It sees the old reference and says, oh, I would like to address it. The loaded value barrier says, okay, let's test if it's a reference. Yes, it is. It tests if it's reachable. No, it's not. Okay, let's get the information from here and update the pointer. That's what it does. Again, the application thread and the collector thread working hand in hand here. This is the difference with these collectors, and that makes it quite fast, because at that moment, when we create the forwarding information in the off-heap page, we can already remove and clean up the physical memory below. And this is not possible with the upper approach, because they first have to update all the references, and then they can remove the old object, but we can directly remove it. Okay, that's quite complex, I understand it. I try to make it as easy as possible. Quick release, done. C4 is only available with Azul Zing, which is our own JVM. But like I said, ZGC very much the same. The response time is high priority. Like I said, we have customers who are using 21 terabyte of heap. It's very good for low latency sensitive applications, for large scale systems, and for highly concurrent applications. So it's only available on Linux or version, which is usually not a problem because most of the people run stuff on Linux anyway. We don't have the performance problem that the other collectors have. The reason for that is we have also not only our own garbage collector, we also have our own compiler in the JVM. And our compiler produces faster code, so we can keep up by producing faster code. It's even with the more intense garbage collection, it's faster than OpenJDK. So that's the difference here. Okay, the big question, which one to choose? We saw all these different collectors, right? We have some essential criteria like throughput, right? We saw that. Latency, that means how fast can your application respond, and resource usage. How much memory does it use, CPU time, and so on. Well, the good thing is it's only 3 points. The bad thing is you have to choose 2 out of 3. So you can't just say, I would like to have all of it. You can say, I would like to have very high throughput and low resource usage. Yeah, but sorry, you will have high latency. And if you say, oh, I need very low latency and low resource usage, okay, throughput won't be good. This is the way it is. And to make it easier for you to choose one, you can also use this chart, which says the runtime overhead increases to the left side, and the pause times increase to the right side. Now you have to choose, and you see already that G1 is in the middle, and that's the reason why it's the default collector, and that might be the reason why all of you are happy, because it works for quite a big amount of range here, except you need really high throughput or very low pause times, then you have to go to the left side. If this is not a problem, but you would like to be restricted on, or you are restricted on your runtime overhead, then you go to the right side, like parallel or serial GC. And this is the time to take a picture. This is an overview about all the different garbage collectors that we have. with their throughput, latency, performance, CPU overhead, and so on and so on. And I hope everybody's still awake, because this is a really dry topic, and I hope you get something out of it. And if everybody took the picture, then thank you for attending, and enjoy the rest of the conference. And we don't have any time for questions, because it's now 0. So if you have questions, just come to me, and I will answer it besides the stage.